Okay, first page of the bookwork for Unit Circle, Section 8A. What is the arc length for 1 radian, which can be written 1 superscript c? Remember from our investigation that 1 radian was formed by taking our piece of string and putting it along the circle's circumference, and the length of that string was the radius of the circle. So in this case, the radius of the circle is r, so the arc length is r for 1 radian. How many degrees in pi radians? Remember that 1/2 of a circle had pi radians, right? You could take that radius string and put about 3 lengths, 1, 2, 3, and a little bit more, 3.14, on there. So how many degrees in pi radians? Half a circle, which is 180 degrees. Convert 1 radian to degrees. Okay, we could take 1 radian, and then we're going to multiply it by a conversion factor. The conversion factor on the bottom is going to have pi radians. And on the top, it's going to have 180 degrees. So the radians cancel out, and we get 180 divided by pi. Let's see what that is. 180 divided by pi. Where's pi? There it is. 57.296. 57.296 degrees is a radian. Very close to 60 degrees, which makes sense, right? Because if you cut up a pizza in 6 slices, it'd be 60 degrees each, and there's about 6 radians in a pizza. Okay, copy and complete giving answers in terms of pi. This is something that you might have done partly in your investigation. Now remember, 180 degrees is pi, 360 is 2 pi, and then everything else is just kind of like halfway in between, right? So 270 would be 3/2 pi, and this would be 5/4 pi, and this would be 7/4 pi. Okay. Now we'll go to the next one. We're going to do units of 30 degrees. So this would be pi over 6, pi over 3. Do you remember that from our investigation? 90 is the same as that one, pi over 2. 120 would be double of 60, pi, 2/3 pi. 150 would be 5 times 30, or 5/6 pi. 180 is pi. 360 is 2 pi. Okay, and so on. Let's see, number 2. Convert to radians, correct to 3 significant figures. Okay, remember that to convert to radians, we need to multiply by a factor. And the factor is going to be 180 degrees on the bottom and pi on top. Okay, so we'll do 36.7, and we're going to multiply by pi divided by 180, and that will give us 0.641 radians. And then 317.9 would be 5.55 radians. Oops, I'm sorry. That goes to that one, right? Okay. Okay. And then 396.7, 396.7. 6.92 radians. Okay, next one. Convert the following radian measures to degrees. So now we are going the opposite way. So now we're going to multiply by the factor pi on the bottom and 180 on top. How do we know that pi goes on the bottom? Well, since we have radians to start with, we want to cancel out the radians, so we put the radians on the bottom. Okay, so we're going to put pi divided by 5. And then we're going to multiply by 180 divided by pi. Get 36. Now you might be able to see that, hey, if I know that pi is 180, so I could just do 3/4 times 180, right? That would be about 3 times what? That would be 135. Or here I could do 180 divided by 9, which is just equal to 20. So I don't need the calculator to do these particular ones. But I do need the calculator to do these, right? Because these don't have pi in them. So I'm going to put 2 radians, and then I'm going to convert it by multiplying by 180 and divided by pi, and get 115 degrees. 0.867. Then I'm going to multiply it times 49.7. 5.267. 301.8, for example. Okay? Okay, page 192, it asks you to read about why does 60 occur so often in angles? And when I say that, I mean like 360 degrees. Inside 1 degree, there's 60 minutes. Inside each minute, there's 60 seconds. On the clock, too, it also appears a lot, but they were talking specifically about angles here. One of the possible reasons that 60 appears often with angles is because it was used by the ancient Babylonians as a base for their numbers. For example, we use base 10, meaning 1-digit numbers represent numbers from 0 through 9, and it becomes a 2-digit number when we represent 10. Or when we represent 100, it becomes a 3-digit number. So the Babylonians would have 60 different symbols, and they would be able to represent the numbers up to 59 with those 60 different symbols, 0 to 59. And then when they got to 60, then they would represent 60 with 2 digits or 2 symbols. So they had a more compact system of representing numbers because they could represent 60 numbers with 1 digit instead of just 10. And because of that, they kind of had an affinity for 60, and then a lot of the main math measures were done with 60. Okay, so that is one of the theories, and it's very interesting. Now let's look at this, and we got 2 pictures of circles, and one has a pie piece taken out of it, or a pizza piece, and the other one just has a slice taken out of it. Now I'm going to go through these different terms, and we're going to mark them on here. So for example, a sector is like this pi piece here. Okay, sector is near and dear to my heart because I worked in the cellular industry for many years, and sector is part of a cell phone tower's coverage. Radius is, of course, that, right? You know that. A chord, maybe you don't remember from like 9th grade, but that's a chord. A center, that's an easy one. An arc, we just kind of looked at arcs just now, right? That could be an arc, right? Major and minor arc. Okay, so like let's say major arc. What's a major arc? A major arc would be an arc that is more than half the circle, like that. Okay, and then a minor arc would be the smaller part. And segment. Segment is like an apple segment or an orange segment. Minor segment would be the smaller part of the apple. And the major segment would be the larger part of the apple. Anybody getting hungry? To find the arc length, multiply the radius times. And if you read in the book, you can see that the arc length, L, is equal to theta times r. Okay, so it's the radius times the angle of the arc. If the angle of the sector is theta, the area of the sector is, it would be 1/2 theta r squared. Okay, these two formulas are given to you in the formula sheet. You just need to remember what's what. R, of course, is the radius. L is the arc length. Theta is the angle of the arc, or the sector. Use radians to find the arc length and the area of a sector of a circle of radius 9 centimeters and angle 7/4 pi. So we're going to find arc length and area of a sector. So first is arc length. L equals r theta, right? So in this case, it would be 9 centimeters times angle 7/4 pi. Okay, so we would just multiply that out, and we would get a length, which would be in centimeters. Okay, now the area of a sector we would give as area equals 1/2, and the theta would be 7/4 pi times r squared, which is 9 centimeters squared. Okay, and then if we multiply that out, we'll get a quantity in centimeters squared, which is an area. Now for this one, it would be similar. So r theta would be 4.93 centimeters times 4.67 radians. And then for A, we would have 1/2 times the radians, 4.67, times 4.93 centimeters squared. Okay. All right, number 3. A sector has an angle of 1.19 radians and an area of 20.8 centimeters. Find its radius. Okay, so we're going to use the same equations, but now the unknown's in a different place, right? So we do know, let's see, we know the area and we know the angle. So we're on our way to finding the radius, right? So we know that area equals 1/2 theta r squared. So if we know the area is 20.8 centimeters squared, and we know that theta is 1.19 radians, then we know that r squared is here, and then we could multiply that out, and we could solve for r, and that would give us the radius, right? What about the perimeter? The perimeter of a sector would be the two radius pieces and the arc length. Okay, so the arc length we find by L equals r theta. We could take the r that we found here and multiply it times the theta, which is 1.19 c, or radians. And then here we would also have two more r's, and each one of these r's is equal to the radius again. Okay, so that's how you would find the perimeter. Number 5. Find theta and radians for each of the following, hence find the area of each figure. So for this one, we would use the formula L equals R theta, because we know the L and we know the R. We just need to find theta. So L would be 6, R would be 8, and theta looks like it would be 3/4, right? 3/4 radians. What about this one? We have L and we have R. So same thing, L equals R theta. L is 8.4, R is 5, and theta is unknown, but we can divide that, and it would be 8.4 divided by 5. Now here, same thing, L equals R theta. This time R is 8 centimeters, and L is 31.7, and theta is unknown. We just divide that out, we can find the answer for theta again. If a sector has radius 2x centimeters and arc length x centimeters, show that its area is x squared centimeters squared. Let's see, so we know the radius and we know the arc length, and then we need to find the theta. So that would be L equals R theta. L is equal to x, R is 2x, and theta we don't know yet. So we divide x divided by 2x, and that would give us theta, and that gives us a half radian. And then if we wanted to find the area of this sector, then we would just put 1/2 theta, which is 1/2 c, and then multiply that times r squared, and r squared is 2x squared. So that would simplify to x squared. So that's exactly what they predicted. Number 9, the end wall of a building has the shape illustrated where the center of arc AB is at C. Find alpha to 4 significant figures, theta to 4 significant figures, and the area of the wall. I think the first thing that we can figure out here is that, well, first of all, this side here is 15, right, because it's half of 30. We can figure out the radius already with the Pythagorean theorem, right? So when we have 5 and 15 here, we know that 5 squared plus 15 squared is equal to the radius squared. So that's equal to 25 plus 15 times 15 is 225 equals r squared. So 250 equals r squared. So r equals the square root of 250. All right. We could rewrite that as 5 square root of 10. The other thing that we can see is that if we extend the line here, if we extend this line, we can make a half circle. And if we make the half circle, we can also see that this angle here is also alpha, right? Because it's kind of a reflection of the top. So that means that the half circle, which is pi radians, can be set equal to theta plus alpha plus alpha. Those all together make 180 degrees. So pi equals theta plus 2 alpha. The other thing that we know is that we could make a little triangle here. This triangle here, we could write it here and we'd have 5 here. This side is 15, and then this angle is alpha. So we could actually use the tangent, which we haven't reviewed yet, but you maybe remember it. The tangent is the opposite over the adjacent, so it's equal to 1/3. And so the inverse tangent of 1/3 is equal to alpha. And to find that, we could turn on the calculator. Make sure the calculator is in radians. So we'll go to the radian mode, and then we'll make sure it's on radian. Normally it's on radian unless you change it to degrees. And then we're going to do an inverse tangent, which is the blue version of this button here. So we'll do inverse tangent, and then we'll say 1/3, 1 divided by 3. And the answer is 0.322. So our angle, alpha, is 0.322. And, they wanted 4 significant figures, so it would be 3218. 3218. 4 significant figures, right? And so alpha is 0.3218, and then theta is equal to pi minus 2 alpha is theta. So that would be pi minus 2 times alpha, which is second answer. So the answer would be, for theta, would be 2.498 radians. Okay, so little c's there to signify radians. Then it asks us for the area of the wall. Now that we know the angles, it's not too hard to figure out the area of the wall. Let's figure out how much this pie shape is here, because we've already done that several times. We know that we can get this area by doing 1/2 theta r squared. And we know that theta is 2.498. It's times 1/2. And then it's times r squared. R squared we know is 5 times square root of 10, or square root of 250. What's the square root of 250? It's 15.8. So it's 15.8. So we can put 15.8 here and square it. Okay. All right. And so that is the area of the pizza-shaped region. Then we just need to add these two triangles here. And actually, if you put those two triangles together, it makes a nice little rectangle. And this rectangle is 5 here and 15 here, so that would be 75 units. So you would just add 75 units, and that would give you the entire area, which would be this whole thing here. Okay? And that's it.